Welcome back. In this video, we're going to look at units in chemical relationships. So we find the chemical relationships in the Chemistry 2026 data book for VCE. It's item 3 on page 4. And you can see that there's quite a few formulas that VCA give you, but they don't have units. And you really need to make sure when you use these chemical relationships that you include appropriate units. So I'm going to show you how you can annotate your data book. So this is item 3 broken down into a series of smaller pieces so that I can show you the units. So small n always means amount of substance in mole. Small m stands for mass, and the unit is gram. Capital M in this context means molar mass in grams per mole. We've got small n meaning number of mole again. C in this formula means concentration in moles per litre or molarity. V stands for volume in litres. N stands for number of mole once again. Number of particles, capital N, doesn't have a unit, it's just a number. But Avogadro's constant, the units are per mole. Small n, once again, means mole. V, just like with gases and liquids, is litres. Molar volume is n litres per mole. The concentration units are already given in the second expression. Density formula. Now, density is a bit of an unusual one. It didn't used to be in the data book until this year, but it's always mass over volume. So whatever the unit of mass is and whatever the unit of volume is, the units are variable, but make sure that you do have a mass over a volume. The ideal gas equation, P is in pressure, is in kilopascals. V, the volume, is in litres. Small n is the number of mole. T is the absolute temperature in Kelvin. And R, we find in table 4, item 4 of the data book. And the units are given as joule per mole per Kelvin. Enthalpy change of a reaction, we'll come back to that in a second. First of all, we'll look at the MCAT formula, Q equals MC delta T. Really important, a lot of students make a mistake with this. The small q, the unit is in joules, not kilojoules. There are 1,000 joules in a kilojoule. Mass is in grams. Specific heat capacity is in the data book. It's 4.18 kilojoules per kilogram per Kelvin, or 4.18 joules per gram per Kelvin, depending on what the other units are. The change in temperature is either degrees Celsius or Kelvin. The capital delta sign means the changing, so the final minus the initial. We can work out molar enthalpy change. It's the Q, which should be joules unless you convert it to kilojoules, in which case, if you convert joules to kilojoules, you divide by 1,000, divided by the number of mole. And then if you're using kilojoules per mole, then the enthalpy change of a reaction will also be in kilojoules per mole. Electric charge, capital Q has got the unit coulomb. I stands for current in amps. T stands for time in seconds. Now note there are two T's. There's capital T, which is temperature, and there's small lowercase t, which is time in seconds. We have number of mole, in this case, of electrons. We have charge, which is coulombs, divided by Faraday's number, which is 96,500 coulombs per mole in the item 4. and we have energy, which is in kilojoules. Just note that that's different to MCAT, which is in joules. The energy there is in kilojoules. The V is for voltage in volts. I is current in amps, and T is time in seconds. Calibration factor, or CF, it's a single term here, equals the energy divided by the delta T, the change in temperature. That's for general calorimetry. Or what we could do is call that electrical calorimetry. It's either in joules or kilojoules per degree Celsius, depending on what the unit of energy is. So that's joules or kilojoules, divided by the temperature change, which is in either degrees Celsius or Kelvin. Reaction calorimetry, also known as chemical calibration, the calibration factor is in joules or kilojoules per degree Celsius. Delta H depends on the units that's used, either joules or kilojoules, divided by the temperature change, which is degrees Celsius or Kelvin. The standard cell potential using the electrochemical series is the E naught of the cell is in volts, the E naught of the reduction half cell is in volts, and the E naught of the oxidation half cell is also in volts. Percentage atom economy, molar mass is always grams per mole. A percentage yield, the actual yield is in grams, divided by the theoretical yield, which is also in grams, times 100. Now, the equilibrium constant has variable units. Sometimes it doesn't have units at all. It just all depends on the stoichiometry of the reaction equation. But the general form of the expression, which is shown in the data book here, is the concentration of the products divided by the concentration of the reactants, where the square brackets means moles per litre or molarity. Now, whether you have units just all depends on the balanced equation. Good luck. You can do this, and see the links to the website in the comments section below. See you next time. Bye.